Morning Year 11. Today we're going to have a look at calculating the different energy stores. Now, I've spoken to a few people and they've said they're a little bit confused about exactly what they need to know for this topic. So I thought I'd group it all together and clarify the 4 key things that we absolutely must be able to do. Before we do that, please have a go at the do now, pause the video, come back and see how you did. Okay, so let's go through some answers. The first question was, what is the equation for gravitational potential energy? It is EP, potential energy, is mass times gravitational field strength times the change in height. Question 2 was, what is the equation for elastic potential energy? So the energy stored by a spring. That was E with a little e for elastic, so elastic energy equals 0.5 times the spring constant, so a measure of how stiff the spring is, times by the extension, the change in length, squared. Question 3, what is the equation for kinetic energy? This one is an E with a little k, so kinetic energy, and that's 0.5 times mass times speed squared. Remember that the mass needs to be in kilograms, this needs to be in meters per second. What is the equation for internal energy? So the change in internal energy, thermal energy of an object when you change its temperature, usually gets given the symbol change in energy, and that's mass times specific heat capacity, which is a property of the material that you're heating, times by the change in temperature. You might see it as delta T, which is what I used yesterday. You could also see it as this symbol here, which is a theta. So either of these is fine. And then 5 is, what is the gravitational field strength at Earth's surface? That is 9.8 newtons per kilogram. So 9.8 newtons per kilogram. Okay, so let's go straight on with the direct instruction. So I've collated these 4 things together. So we have the idea of kinetic energy, which is talking about things that are moving, and that uses this equation. You have elastic potential, so that's energy stored by something that's been stretched or squashed, just like you can see in the diagram here. If you climb up a mountain, this one's Mont Blanc today, you gain what's called gravitational potential energy. The higher you are, the more gravitational potential energy you will have. And then finally, yesterday we had a look at internal or thermal energy, so the energy change if you increase or decrease something's temperature. And let's go through a few quick examples for this one. So if you are asked to work out the kinetic energy of an object, you'll be given a mass and a speed. So in this instance, I've got a cyclist with a mass of 72 kilograms and their speed is 12 meters per second. We always do exactly the same, so we'll do kinetic energy. We'll write the equation 0.5 mv squared, a half mv squared. You can either use the 0.5, that makes it a little bit easier, or you could use the half symbol like they do up here. So that was 0.5 times by the mass of the cyclist, which was 72, times by the speed of the cyclist, which was 12, and that needs to be squared. So again, you get given the mass, you get given the speed, pop it into this equation, and it's super straightforward. I'll type that into my calculator as quick as I can. 5,184 joules. So 5184 and a capital J for joules. That's my answer there. So again, very, very straightforward. You record the equation, write it down, substitute in the values, there's your answer. So kinetic energy, this is something that is moving. If they ask you about elastic potential energy, they're going to be talking about something that's either getting squashed or stretched out. And we also spoke about this idea of the spring constant, which is, this is how stiff the spring is. So a high spring constant means it's very stiff, it's hard to stretch. A low spring constant means it's not very stiff, so it's really easy to stretch out. The equation is E equals a half ke squared. So K is the spring constant, E is the extension, that's the change in length. So as always, we'll write the equation, even if it's straight above, always write it down. 0.5 KE squared. This time our spring constant is 0.5 as well, so we have 0.5, the half, multiplied by the spring constant, 0.5, multiplied by the extension, and this one has stretched 12 meters, and it's the extension squared, so I'll put a little 2 up there. So again, type it into the calculator, 0.5 times 0.5 times 12 squared gives me 36 joules. And underline it to show that's what we're talking about. So if we stretch this spring by that much, it will store 36 joules of energy. So there's not very much energy stored in that spring at all. The next one is your potential energy due to your position, your height in the gravitational field. So when we looked at it on its own, we looked at the Matterhorn. This one is Mont Blanc, so this is higher than the Matterhorn, but it's still one that I've been up, you'll be pleased to hear. And its height is 4,810 meters above sea level. So back then my mass was 80 kilograms. So let's see how much energy I gained when I went from sea level up to the top of Mont Blanc. So I'll write the equation, EP equals mg, and I'll put a delta in to show that I changed my height. I went from sea level to the top of this mountain. 80 times 9.8 times 4,810. 80 times 9.8 times 4,810 gives us 3,771,040. If you can hear some noise in the background, that's just a dog walker bringing Molly back. Sounds like she was a bit crazy. The dog, not the dog walker. So 3,771,040 joules. So that is our gain in potential energy. Thermal energy, the last one we looked at. So this time we'll use delta E, so the change in thermal energy. That's mass times by specific heat capacity times by the change in temperature. So 1.5 times 4,200 times by the change in temperature. So we have to do a little bit of extra work here. We've got an initial and we've got a final, so we need to work out the difference, how much it's increased by. So I'll do the final temperature, 100 minus 25, and that shows that the increase in the temperature has been 75 degrees Celsius. So 75. So 1.5 times 4,200 times by 75. That gives me 472,500. 472,500, and the unit is joules. So again, we're just summarising the 4 different calculations that you need to be able to do. So if it's moving, you'll be working out kinetic energy using the mass and the speed. If it's stretching, you're going to be using the half KE squared, so you need to know the spring constant and how far it's stretched. If you're moving up or down something, it will be gravitational potential, which will be m times g times the change in height. And then finally, thermal energy or internal energy. If you're changing its temperature, you can work out how much the internal energy has increased or decreased, but you will need to know the specific heat capacity of that material. Okay, so based on what we've just done, there are a sequence of questions. You just need to decide which equation we're going to use and substitute in the values. Once you've had a go at all of these, there are some answers towards the end, so work through these, get answers where you can, and then check what you've done against the answers at the end. Thank you very much.